Now that we've applied Kirchhoff's rules to DC circuits having a constant current in time, we're going to apply them to a specific type of DC circuit, DC meaning the current is always flowing in one direction. But in this case, that current will be allowed to change with time. We'll talk about the reasons why the current changes. So we'll have our voltage source here, V, a resistor, and a capacitor, hence the name RC circuit. We will study the RC circuit when they are wired in series. When they are wired in parallel, the circuit becomes much simpler and less interesting. You can think about that on your own. Microscopically, what do the electrons want to do here? Okay, when this initially uncharged capacitor is connected to the battery in a circuit, we said that electrons will start to move this way. They leave behind positive charge on the upper plate of that capacitor. Now these electrons experience resistance in the circuit, whereas before we were simply considering a capacitor wired with perfect wires to the battery. Now there is resistance present, and we'll see that that slows down the process of charging the capacitor. The electrons experience resistance. They are pushed back once they reach the battery to the lower plate of the capacitor. And this process will proceed. Now it will take some macroscopic amount of time, and in general we want to allow that the current flowing in the circuit from higher to lower voltage will be a function of time. It will not have a constant value anymore, so we're going to use a lowercase I for that current. Our initial conditions say at time equal to 0, the voltage across the resistor and the capacitor are what? Well, we said the capacitor was initially uncharged. Following the loop rule, if this voltage drop was initially 0, then all of the battery voltage was applied across the resistor. Let's write down the KVL for any time during the process of charging that capacitor. So the KVL, or loop rule, there's only one loop in this circuit, so it's pretty simple. We'll start here, and we'll say plus the battery voltage, that's a constant in time, minus the IR, Ohm's law, for the resistor, minus, again, because we're traveling with the current, going from higher to lower voltage. Let's just specify that our loop direction is clockwise here. What's left is the voltage across the capacitor. We need to remember our relationship between charge capacitance and voltage. And I'll label this as VC just to remind us that applies to the voltage across the capacitor. We already used Ohm's law for the resistor. These are sort of the steady state rules that we've been using. Now we're going to extend those to be valid at all times during this process. So Ohm's law holds at any moment in time. As well, now the voltage across the capacitor, since we're going from a higher to a lower voltage, right? This is the positive plate, this is the negative. We subtract Q over C. C is just the constant property of the capacitor, and Q is the instantaneous charge on either plate, the magnitude of charge. And now we're back to where we started, so the loop rule says this sums to 0. Well, you look at this and say, how are we going to solve for the charge on the plates as a function of time? We're going to need the relationship between current and charge. We've discussed that at length. This is current is the time derivative, d by dt, of the charge flowing through any point in your circuit at any given time. And that will be constrained to land on the capacitor. So the current thought of as flowing through the circuit is depositing some amount of Q per unit of time onto the plates of the capacitor. Let's rewrite the equation then, our loop rule. We'll say battery voltage at all times is dq dt times R. Just push these over to the right, plus Q over C. What you see here is a first order separable differential equation. We do not require you to solve differential equations in this course, but you have seen similar equations in previous physics discussions, and we'll talk about its solution here. So we have the following procedure to solve a separable first order differential equation. Here we're trying to solve for the function Q of time, is to separate all of the items depending on Q will go to the left-hand side. All of the items that are either independent of Q or related to time directly will go on the right-hand side. So at first I have V minus Q over C divided by R is equal to dq dt. I need to cross multiply and then separate these things. Okay, so I have V minus Q over C dt is equal to R dq. Then I will push the dq to be in the same term as our V minus Q over C. Then we have a dt over R on this side. This is not quite the nicest form of things. What we like to do is multiply each denominator by the capacitance. So we have dq over CV minus Q is equal to dt over RC. And I will swap the minus sign in this denominator here. You'll see why in a bit. So we have dq on Q minus CV is equal to negative dt over RC. We call this a separable differential equation for a reason, because I've been able to separate all of the Q dependence on the left and all of the time dependence on the right. And now we integrate both sides. Again, this is the theory behind the charging RC circuit. You do not need to know how to derive this, but I think it's valuable to see where the formulas come from. And we have to integrate carefully here. We have dq over Q minus CV is equal to integral minus dt on RC, and we need to specify limits of integration. So say we're integrating from a time of 0 up to any generic time during the charging process. That means I should specify a dummy variable of integration t prime. I'll do the same thing on the left-hand side. The capacitor began with 0 charge, and it will end up with some amount of charge, lowercase q, after a time t. So we'll specify q prime variables of integration. What do we get in this process? We have the natural log of the absolute value of q prime minus CV. We need to evaluate that from 0 to q equals integral of minus dt prime is just minus t prime over RC. We're very close to a solution now. We have the limits to evaluate at the natural log of Q at the upper limit. That's the charge at any time t, minus the natural log of absolute value 0 minus CV equals this thing. I'll take the minus out front, t over RC minus 0 over RC. Okay, that's just 0, of course. We'll combine our logs here. So the difference of the log is the log of the quotient, Q minus CV divided by negative CV, and that equals negative t over RC. Well, at any time t, if this is your fully charged capacitor, CV, right, we used the battery voltage in this derivation, so CV represents the amount of charge when the capacitor is fully charged, C battery voltage V. At any time, lowercase q has to be smaller than its final value. Does this make sense? Yes. Okay. CV is the maximum value of Q. So this quantity here, Q minus CV, is negative. when you divide by negative the maximum charge, you have a positive number sitting there inside of that absolute value bracket. So we could rewrite this without the absolute value. You must keep the same argument. We've just argued that that argument is positive. Q at all times will be less than CV. Now we need to invert or undo the natural log. And we do that by taking E raised to both sides of the equation. Of course, E to the natural log of this argument is just the argument, Q minus CV over negative CV. And on the right-hand side, we have E to the negative time over RC. Now we've done it, and we should start a new sheet of paper. Circuits Theory, page 1. RC circuit charging. Page 2. What do we have now? We have that Q minus CV. We're multiplying the negative CV to the other side of the equation. We are now going to rewrite bringing back the explicit time dependence. Q of t is equal to, push this, we'll add CV to both sides of the equation. So now we have CV minus CV e to the minus t over RC. And the simplest form now, we can write Q as a function of time. The charge magnitude on either plate of the capacitor is CV times quantity 1 minus E 2 minus T over RC. And that is the solution to the differential equation. You may see this written at times with the equivalent expression CV replaced with this symbol called Q infinity. Meaning, if you wait an infinite amount of time, that is the total charge on the capacitor, its capacitance times the battery voltage. Let's plot this function. Charge as a function of time. We start out again with an uncharged capacitor. And what does this function look like? Well, at t equals 0, again, we must obtain a zero charge, is e to the 0, 1. Yes, it is, so 1 minus 1 is 0. We're good there. How about an infinite amount of time later? E to the minus infinity is 0. If you ignore this part, then you get the Q infinity, which is the sort of final or asymptotic charge on the capacitor. So that value, Q infinity, is, again, capacitance times the battery voltage. How do you get from here to here an infinite time later is essentially upside down exponential decay. Okay, don't call it exponential growth, which would be like this. it's a constant, CV, minus exponential decay. So as time goes on, the amount that you subtract from the constant gets smaller and smaller and smaller until there is some effective time later where you've reached the total charge. Remember, there is a direct relationship between current and charge. We'll look at that in just a moment, but first we want to define something which is sitting here in the argument of the exponential, which is called the time constant. We use lowercase Greek letter tau, and it is equal to the resistance in your circuit times the capacitance in your circuit. It's a shorthand that lets you write this as e to the minus t over tau. Let's make sure we're clear about its units. The units of RC are the ohm times the farad. Remember, an ohm is a volt per amp, and a farad is a coulomb per volt. Volts cancel out and you have a coulomb per amp. An amp is a coulomb per second. So the coulombs cancel out and we get seconds are the unit of the time constant, as we would expect given its name. The current in a charging capacitor, or rather the current in the circuit, is found easily then at any time t. Remember, it's just dq dt, so we can take one time derivative of that expression and I'll use the shorthand with the time constant, tau. All right, CV's constant coming out front. I have the time derivative of 1, 0, minus the time derivative of e to the minus t over tau. So you'll recall the derivative of the exponential, you multiply out front by the derivative of the argument, that's minus 1 over tau, and then you keep the exponential function intact. You see that there will be some cancellation here of minus signs. So our current as a function of time is CV over tau e to minus t over tau. But what is tau? It's RC. So the capacitance will cancel out, and you end up with battery voltage V divided by resistance R e to minus t on tau. And that is the most compact way of thinking about the current flowing in your charging capacitor circuit. Let's be sure to visualize that. Of course, if it's the time derivative of this quantity charge, we are literally plotting the slope of this function over time. That slope, you can see, is always positive, but it's getting flatter and flatter, closer to a zero slope after an infinite amount of time has elapsed. Of course, if you just look at the function itself, you see it's representing exponential decay. What do you think the starting value of the current should be naturally? When time is 0, e to the minus 0 is 1, and the starting current is just the battery voltage over R. That's good. It makes sense. I could even call that I0. You're going to use this in the lab experiment, this idea that the initial current flowing in your circuit will be just the battery voltage divided by resistance, which tells you that the capacitor in that initial instant of time behaves almost like a wire is sitting here. It's like a short, because electrons are free to just flow off of its plates at that first moment in time. It looks almost as if we're just having a simple battery resistor circuit at time equals 0. Okay, so we have exponential decay, which would reach 0 current an infinite amount of time later. Let's talk briefly about an example here. For the charging capacitor, how do we use the formula that we just derived to answer a question such as this? How long will it take for the current to fall by 99%? Or stated another way, find the time, say with a subscript of 1 over 100, when the current at that time is 1% of its initial value. Start with your expression for current. I as a function of t is I0 e to minus t on tau. In this example, we want the current to be 1/100th of its initial value at the time, which I called t 1 over 100. The starting currents cancel out, and we need to undo that exponential with a natural log. So you have log 1 on 100 is negative t at that time over tau. And we have simply that the solution for that time is tau natural log 100. Okay, I've skipped the step that, of course, the natural log of 1 over 100 is negative log of 100, so our negatives cancel out. And it is perfectly acceptable, right? If we ask you, how long will it take for something to happen, and we haven't told you anything about the circuit, we haven't given you the resistance or the capacitance, you don't know the value of tau in seconds, but it's perfectly acceptable to say we will drop 99% of the current once something like 4.605, that's the natural log of 100, time constants have elapsed. All right, this is an amount of time in seconds. It's perfectly okay to leave your expression in terms of tau, so long as we didn't give you any of the circuit element values and ask you to specify the time in seconds.